Hi, I'm Oscar Guarnizo, and today I'm going to present you the preliminary results of convolutional neural network feature extraction using covariance tensor decomposition. Deep learning has made significant advances in computer vision applications by enabling features to depict multiple levels of abstractions. Nevertheless, despite the outstanding research in this area, effective learning critical depends on the expertise and empirical observation for tuning hyperparameters and architectures. In this context, an attractive alternative to enhancing conventional convolutional neural networks is to understand the effects on multilinear algebra methods to generate kernels. In this context, this work introduced a new algorithm known as covariance tensor method, based on tensor decomposition for feature extraction. Our method works directly from high-order tensor representations, capturing multiple interactions between the tensor. Starting from an input, which can be an initial dataset or an intermediate batch of feature maps, we take each image and extract some patches. The extracted patches are composed into a 4-order tensor, which allow us to get a covariance tensor. This covariance tensor allows us to get the relationships between different patches in the tensor. We perform the same process over all the examples and obtain a mean covariance tensor. Using this mean covariance tensor, we can get a core tensor by Tucker decomposition. But first of all, we need some factor matrices. So we unfold the mean covariance tensor with modes 1, 2, and 3. Then we apply a singular value decomposition to finally obtain our factor matrices U. With these factors matrices, we can obtain an approximation of the core tensor with the following equation. The core tensor encapsulates some relevant features of our dataset, so we propose to rearrange these features into block-wise kernels. Finally, we plug our kernels into convolutional layers for classification tasks. The results were some kernels which could be used for different applications. We particularly evaluate 2 applications: direct inference using these kernels and initialize using these kernels. As we can see, the results were promising and comparable to state-of-the-art findings in CIFAR-10. For future works, we still need to elaborate further experimentation with deeper networks and large dataset, and probably contemplate other applications. Thank you very much for your attention.